Okay, this is question number 6. It's where we've got a capacitor charged to 60% of its maximum voltage in 0.9 seconds, and they want to know what the time constant is. So these ones, you need to sort of know the formula for that charging thing so you can work it out exactly. And if you don't, go back to my little video on the functions for the charging and discharging curves. So this is a circuit. It's the usual circuit where we've got a voltage charging up a capacitor. The curve, as you will know, looks like this. It's charging up to that EMF. Now the function, we already have gone over that, like I said, is going to be one of those functions where that little torr thing is the time constant. So what's it asking you? This is a critical point, always a critical point in a physics question. How are we going to set it up? And what they're saying is 60% of maximum voltage. Well, this gives you the voltage. So they're saying 0.6 of that maximum voltage will be equal to that. So if the maximum voltage is E, then 0.6 of E must be equal to E times 1 minus E to the minus T over 4, right? Right? So 0.6 of that has got to equal that. When that equals that, we will be able to figure out the time constant because we already know the little t is 0.9 seconds. We're pretty much already there, except for a little bit of algebra and a little bit of dealing with logs. So let's hope you remember your log stuff. We can obviously cancel out these maximum voltages. We don't care what that is. So we didn't even need to know what the maximum voltage was to work this out. We can now say then that 0.6 equals 1 minus e to the minus t over that little torr. Minus 1 from both sides, got minus 0.4 equals minus e to the minus t over that. So we can cancel out those minus signs too. And what we'll do is, when you've got an e, if you take the natural log of an e, it disappears. Hopefully you know what logs are, right? Logs are where we have a base 10, base e, and we basically convert numbers into the exponents that would be on that base to make that number. It's really nice. So when you multiply things, two numbers, all you have to do is add the logs together. And if you divide a number, all you need to do is subtract that log from the number that's divided into it. It's really beautiful. So what are we going to do here? We're going to take the natural logarithm of both sides. You can put that in brackets if you like. And the natural logarithm e to the minus t over that little torr. So that's all going to disappear now. So we've got in of 0.4. I call it in, I don't know. You can say natural logarithm. I like to just call it that. Minus t all over that little torr baby. And we're getting a bit closer here because this is what we're after. We're after the time constant, right? And we're definitely getting a bit closer to that. So I'm thinking right now what we want to do is go bring that minus across to that side, just times minus 1 by both sides, and then what we can say is that, you know, when you've got a log, if it's got an exponent, you can bring the exponent down to the front of the log. And that's because, sort of like if you had the log of 100 squared, the log of 100 squared is the log of 10,000, which is 4, but that's just like 2 times the log of 100. So you can actually just multiply the whole thing by the exponent. It's again another one of those beautiful parts to logs. So we can actually write that as the in of 0.4 to the minus 1, if you like, equals t all over that torr. So, but we all know that in of 0.4 to the minus 1 is the in of 1 over 0.4. So I'll bring that all down there so that we can actually solve it, and we'll have time constant will be equal to t, which is 0.9, all divided by the natural log of 1 over 0.4. Hopefully you saw it, because it's minus 1. Remember minus 1? We're doing that since year 11, saying that's equivalent to dividing by it. So if we solve this, put it all in our calculator, we'll come out to the time constant being 0.98 seconds, and we're done. The reason I've put this example here is that little bit of logarithmic stuff and that sort of thing. We're done.